All right, so welcome again to our lectures on algebraic topology. I'm Norman Wildberger, and now we're going to talk about more aspects of the sphere. In our last lecture, we talked about the sphere and stereographic projection, and we introduced the idea of the inversive plane. I want to connect now the inversive plane with the sphere using stereographic projection. So let me remind you that with inversive geometry, what we had is we had a circle. It was a rather arbitrary circle, and we had the idea of inversion in the circle, sending a point x to another point x prime. So the inversion in the circle takes x to x prime with the property that the distance from O to x times the distance from O to x prime is the square of the radius of the circle. And to make that work, we needed to add an extra point at infinity off somewhere so that the origin, or the center of the circle, could get sent to the point at infinity. And now the ordinary Euclidean plane together with this point at infinity is the domain of inversive geometry. And we can talk about the properties of this inverse operation, and it has some pleasant properties. So let me just list them. The first property of inversion is that it sends circles / lines to circles / lines. So for example, if we had a little circle over here, then its image would be another circle. And if we have a line, say this one here, then its image is going to be also a circle. It's going to be a circle, however, that goes through the origin, because this line kind of meets this extra point at infinity, and that's sent to the origin. So the image of this is going to be a circle which is going through this point, and this point, and this point. And there's only one such circle. And so that's what it must be. So that's the first property. And then the second property is that I sub c is conformal. Again, that means that it preserves angles. So that if we have two circles, say another one right here, and look at its image, then the angle between these two, where they meet, that angle there, is going to be equal to the angle between these two where they meet, that angle there. That's theta, and that's going to also be theta. So these two properties are, of course, very parallel to stereographic projection, and it turns out that stereographic projection can be viewed, in fact, as a type of inversion in a higher dimensional space. So it's not entirely surprising that, that these two things are connected. But I'm not going to mention that. So this is inversive geometry, but now we can connect it with the sphere. So the inversive plane is really topologically equivalent to our tooth sphere, because we have the usual plane and one point at infinity, and the stereographic projection makes that correspondence obvious. Let me just remind you what that goes. So here's a sphere, and it's equatorial plane, and a south pole. And if we're given any circle, say in the plane, then we can project that up. We can project any point on the plane to a point on the sphere. It's a little bit hard to visualize. this is supposed to be a point on the plane, and this is a point on the sphere. And this is a circle in the plane, and this is the corresponding circle on the sphere. And a lovely fact that happens now, it's very interesting, is that the geometry of the inversive plane, which is really this plane here, plus an extra point, can be closely connected with the geometry of the sphere. Because we now have a matching of the plane with all of the sphere except for that point there. And so it's natural to call that point infinity. And now we're off to the races. We have now the inversive plane acting like our sphere. So now it's a natural question is how do we think about inversion in a circle on the sphere? We know how to invert in this circle here. So we know that this point x gets sent to that point x prime when we invert in that particular circle in the plane. So we can now ask, well, how does all that transfer when we transfer it to the sphere via stereographic projection? This circle here, let's call it C, gets sent to this circle here, let's call it C tilde. X gets sent to, so say, point x tilde, and x prime gets sent to some other point on the sphere, say x prime tilde. So a natural question is there some idea of inversion in a circle on the sphere that starts with x tilde and sends us to x tilde prime? So, is this inversion in C tilde? Well, the answer is yes, and the solution is very pleasant and interesting. So what happens here is that if I just draw our sphere again without all the other stuff, and I draw a circle which is on the surface of the sphere. Okay, so that's the intersection of the sphere with some plane. Then what you can do is you can associate to that circle a cone, the tangent cone. Imagine like an ice cream cone. If you have a circle and a sphere, and you have a little circle on it, you can just look at the lines which are tangent to the sphere through that circle, and you will get a cone meeting at a point there. So the tangent cone to the circle has an apex or a vertex to a circle on the sphere, has a vertex. Let's call it V. And then it turns out that the inversion in the circle, let's call the circle C tilde as we did before, then the inversion in that circle can be defined purely in terms of this vector, this point V. So I of C tilde can be defined.
So can you explain how you make the tangent cone again?
Yeah. So if you let's say that there's a sphere, okay, and you have your eye right here, and you're looking at that sphere, okay. So the boundary of that sphere, the part of the sphere that you see, will be a circle which goes through that point and that point. Do you agree? Mm-hmm. It's exactly a cone. The cone that you get by starting from your eye and the smallest cone containing the sphere. So that's what I mean by that point will then be the vertex of the cone generated by that circle. That's the relationship between the circle C tilde and the cone's vertex V. All right, so what we can do now, once we've got this vertex outside, determined by a circle, is we can use it to match up points on the sphere. Namely, we can draw any line through this vertex that intersects the sphere, and that will intersect the sphere in 2 points. Okay, well, actually this is not such a good picture. This should be bigger. This thing should actually be closer here. So let me draw it a little bit better. So the vertex should probably be here, and I will draw the line like this. And it will intersect the sphere in 1 point inside the circle and 1 point outside the circle, perhaps around the other side. And that defines a mapping between the point x and the point, or maybe x tilde to make it match with that, and the point x tilde prime. So this inversion in the circle can be defined by using lines through the vertex V to match up points x tilde and x tilde prime on the sphere. So it turns out, it has to do some work to check all these statements, but it turns out then that the inversion in the plane, the original inversive geometry in the plane, when we transfer it to the sphere via stereographic projection, then ends up having this interpretation of being reflection from this particular external point, interchanging inside and outside of circles. So it's quite a different view on what's happening with inversive geometry by going from the plane to the sphere. In some sense, inversive geometry lives on the sphere more naturally than it does on the plane. So sort of the moral of the story. All right, so now let's have a look at another subject which is also closely connected with this and goes back right to the roots of algebraic topology and complex analysis. And we'll go back to another interpretation of the sphere due to Riemann, the Riemann sphere. When you study complex analysis, we are studying functions in the complex plane, 1 and I, and 2 plus I, and so on. Well, this is just the ordinary plane, but Riemann realized that for many purposes it was better to think of the complex plane as being augmented by an additional point. Okay. So Riemann's idea was, let's take the complex numbers, in the sense of the usual plane, let's add a point at infinity. And this point at infinity is meant to be sort of in all directions. Any direction that you go, you bump into this point at infinity in sort of a limiting sense. And that's going to be topologically a sphere, which has, in fact, a complex structure. That's called the Riemann sphere. And we can visualize it by essentially doing stereographic projection, just like we've been talking about here. So we can take the complex plane with its x and its y coordinates and lie it sort of horizontally. We can find there's 1, and there's -1, and there's I, and there's -I. And the unit circle lying in that plane. And what we can do is we can stick that all in the three-dimensional space by introducing another axis, say the z-axis. and introducing the sphere, which is centered at this point. Okay, so now we're talking about the sphere. The unit sphere with coordinates x squared plus y squared plus z squared equals 1. And we can do exactly what we've been doing. We can project from the south pole, which is just as it was before. So there's 0, 0, minus 1 again. And we just perform stereographic projection. That was that map P that we defined earlier. P from the plane. But the plane is now the complex numbers. That's the equatorial plane, to our two-sphere. So the picture that we get is that our complex number plane is now sitting on the surface of a sphere, which may be a little bit odd. So here's the complex sphere. So where are the various points? Okay, there's the center. So there's the North Pole, which will be 0. You just have to think which way things go. The zeros are in the middle. If we go straight up, we hit the top there. So that gets to be 0. And let's say the point coming towards us here, that's the point 1. And the point on the opposite side would be minus 1. And the point at right angles here, that would be I. And the point on this opposite side would be minus I. So the usual interior of the unit disk, the inside of the unit circle, will be the northern hemisphere, the upper hemisphere. And everything outside the unit circle will be the lower hemisphere, with the south pole being our extra point at infinity that we had to add. All right, so this is another picture of complex plane. But Riemann realized it was a very good picture for a number of reasons. And that is not a course in complex analysis, but we'll just mention that a lot of functions, which is after all what you study when you study complex analysis, you study functions of a complex variable. For example, let's take a simple one, z squared. That's a function from the complex plane to the complex plane. And it has the additional property that's actually extendable to infinity. If you take a very big complex number and you plug it into this function, you're going to get output another very big complex number. So infinity is naturally sent to infinity. In other words, this function extends to a continuous function from the Riemann sphere to itself. So f extends to a continuous function from the Riemann sphere to itself. Okay, so this is really worth thinking about, especially if you've done a complex analysis course, which I presume many of you have. Okay, so here's a problem to think about a little bit. Problem number 7, I believe. So explain what the map f of z equals 1 over z looks like in this picture. Looks like as a transformation of the Riemann sphere. In ordinary complex analysis, we say that the function f of z equals 1 over z is undefined at 0. We say it blows up. But now we can say, well, it's not really that bad. All what's happening with 1 over z is that 0 is going to infinity, and infinity is going to 0. It's not that crazy, and it's rather continuous. As a point approaches 0, then its inverse is going to approach infinity. So it's a nice transformation of the sphere. Maybe it's a rotation, or maybe it's a reflection, or something like that. So you have to figure out what exactly it is. And what about this, let's have another look at this example, f of z equals z squared. What does that do to the sphere? Let's have a think about what the function f of z equals z squared does to the sphere. Well, let me remind you a little bit about the squaring operation in complex number plane. Okay. So if you have the unit circle, and we're working here in the complex numbers. Okay, and we're just talking about the squaring operation. So f of a plus bi is going to be, by definition, a plus bi all squared, which is a squared minus b squared plus 2abi. That sound right? Yeah, that's the map. Okay, so what's it do? Well, it sends 0 to itself. It rotates the unit circle. Okay, so if we have a point z here, then at an angle theta, then z squared will be at an angle 2 theta. Okay, so it's rotating here, and well, if you have a point outside here, then what's happening is it's not just rotating it, but it's also dilating it as well. Because the modulus of z squared is the modulus of z all squared. So this modulus is getting bigger, but if we had a point inside, then the angle would double, but the modulus would be also squared, so it would be getting smaller. So points inside are sort of rotating and shrinking towards 0. Points outside are rotating and shrinking towards infinity. And if you look at the image of the circle, well, because this is a doubling map, as z goes once around the circle, z squared, as we've seen before, will go around twice. And this was a very important realization for Riemann. He realized that the squaring map on the Riemann sphere ended up being like an onion with 2 layers. So if you take the image of the sphere and you think of the function as acting on the sphere to itself in some sense, then what happens is as you go around, the image goes around twice. And if you have a circle or a half circle between 0 and infinity, then if you look at the image of that, then that sort of sweeps around twice. Because the origin and the infinity are both kept stationary by this map. So although we're rotating in the middle, the outsides are stationary. So you kind of, if you imagine like a curtain, perhaps a curtain with a slit, then what happens is that roughly what's happening is that you're going around twice. You're revolving twice around with this onion. So, and what Riemann realized that is that the image of this function can be thought of in terms of what's now called a Riemann surface. What you can do is you can take what you're really doing is you're taking 2 copies of the sphere. It's a little bit hard to draw, but there's one copy in white, let's say, and another copy, another onion layer, let's just say really very close but just inside it. So imagine having two copies of the sphere, two layers, one in white and one in yellow, but just inside. But now we're going to combine these two. How? Well, by slicing. So we're going to slice the white one from 0 to infinity. And we're going to slice the yellow one from 0 to infinity. And then the image can be thought of in terms of gluing these two shells together. Okay, so let's see how this goes. So the white one is on the outside, the yellow one's inside. Just imagine we have two spheres inside, and they're both slit from 0 to infinity with the slits right on top of each other. Now as we go around, suppose we start on the white surface, and we go all the way around, and we're almost back to where we started with. But instead of keeping on going, we get to the slit. What we do is we just hop onto the yellow sheet at that point. We glue the white slit on the outside to the yellow slit inside and keep on going. Okay, so now we're on the inside on the yellow slit, and we're going around, and when we get to the other edge, there's the free end of the yellow sheet. But there's still the free end of the white sheet that we haven't glued. We just hop onto that one. So these two kind of get interleaved. The white, as we go all the way around, and the white sort of jumps to the yellow one, and then when we go back around and we get to the other side of the yellow one, we jump back to the white one. And that surface, in some sense, represents this function, f of z equals z squared. In particular, it allows the definition of the square root function. That's what was actually quite interesting. So the square root function, although the square root function is problematic on the usual sphere, because there's two square roots, but rather on this augmented or two-skinned sphere, the square root function is well defined. And it was really this kind of thinking about the complex plane that led to the subject of algebraic topology. Because eventually people realized that this surface that we've drawn here in this rather convoluted way can be thought of in another way. We don't have to have the shells inside. We can move them apart so that we can see more clearly what's going on. Okay. What we are really doing topologically is this. So what we are doing here, if I redraw this picture, we have one sphere with a slit. Okay, so we've sliced, that's a sphere, and we've slit it. And then we have another sphere with a slit. There's its slit. Okay, and we're going to glue this in such a way that okay, this point A is going to go to that go to that point A, and then as we go around, this point B is going to be glued to this point B. All right. So what we can do to make that a little bit clearer is we can open up the slit. So we'll take this picture, we'll take our white sphere, and we'll open up the slit so that it's a nice little circle. So it's actually a hole on the surface of the sphere. Right? If I cut the sphere and then I just open up that hole, I've got now a nice little round hole. I can just make it round. And I can do the same thing with this one here. There's a sphere. And I take the slit and I just open it up. So now I have a hole in this one. Okay, now I still have to sort of glue these things together. And so I've gone from here to here. And now let me go up here. So now what I'm going to do is I'm going to take this sphere here that I had, and I'm going to enlarge this hole so that it's actually coming out. So it's like a little volcano. Okay, I'm pushing it out from the outside so you can actually see it on the outside. All right? It's like I've grabbed it and I've moved it. Remember, we can deform things like as much as we want. And over here, we'll do the same thing to this one. So we'll take this hole and we'll push it out also, so we have a nice little tube coming out. And now what are the instructions? Well, the instructions are to glue these two things together. We have to glue one side of this to this one side of this, and the other side of this to the other side of this. That ends up amounting, once you look at it carefully, to simply gluing those tubes together. And so the result of that is, well, if you allow me to sort of tilt it a little bit. So we've got one sphere like that, and then we've glued it to another sphere like that. And what's the resulting object? It's another sphere. It's still a sphere. It's just a sphere with we've sort of squeezed a neck out of it. But if we allow this to blow up and we pumped air through it, it would become rounder again. It's still a sphere. So it turns out that this function f of z equals z squared, which you've seen in complex analysis a lot, it's really associated in a very natural way with a geometrical object, namely this Riemann surface. That's somehow the domain on which it really lives in some natural sense. And topologically, that Riemann surface is, in this case at least, a sphere. But it turns out for more complicated functions or more complicated relations, you don't get necessarily a sphere. You can get more interesting topological two-dimensional surfaces. And so this was one of the key, I suppose, motivating problems for algebraic topology in the 19th century. Understanding Riemann's thinking about topology connecting with complex analysis.
So there isn't a Riemann surface. There is a Riemann surface associated with each.
Associated with the function. Yeah, or in fact, you don't even need a function. You could also have a relation, like instead of thinking of like y equals z squared, you could have a relation like y squared equals z minus 1 times z minus 2 times z minus 3.
Right.
That also, once you think about it carefully, generates a Riemann surface. And I think in this case it's a torus. I might say more about that at some point. All right, we have not exhausted yet our manifestations of a sphere. There's another very important way in which a sphere arises in mathematics, which is the sphere as the projective line over the complex numbers. So in other words, S2 is also, can be interpreted as the projective line P1 over the complex numbers. So let me remind you what we did a few lectures back. So a few lectures back we were considering P1, just ordinary P1. And what was that? That was the space of all one-dimensional subspaces of A2. And although I didn't say it, we were really working over the real numbers, or I prefer over the rational numbers. And the picture that we had is we were working in A2, our two-dimensional plane. And all the one-dimensional subspaces form this pattern of bouquet of lines through the origin. And then you may remember that we decided that space of all lines was topologically a circle. Remember that? So we said, oh, we could put a circle in just like that, and that labeled all the lines through the origin. So that the P1, the space of all one-dimensional subspaces of A2 over Q, that was really the same as a circle. Now we're going to look at that same situation but complexify it. We're going to complexify that same picture. So we look at the same thing. We do the same over the complex numbers. All right, so let's see how that goes, and let's see why we get a sphere. All right, so what do we have to do is we have to start with our two-dimensional space, and to make it clear that we're talking about two-dimensional complex space, let's call it C2. Okay, we're working with C2, and C2 consists of things of the form ZW, pairs of complex numbers. Z and W belong to C. And we can kind of think about it like this. We can kind of think that there's one copy of C in this direction and one copy of C in this direction. And if there's a Z here and there's a W here, then this point is somehow ZW. But this is not a very good picture because C is not one-dimensional. C is actually two-dimensional. It's actually two dimensions in this direction and two dimensions in this direction. We would really need 4 dimensions to visualize this properly. Okay, but this still gives us a reasonable idea of what's going on. Okay, so what we want to do now is we want to look at one-dimensional subspaces in this. This is the two-dimensional vector space if you want to think in terms of linear algebra. It's a two-dimensional vector space over the complex numbers. We're interested in what are all the one-dimensional subspaces. Okay. So how do you get a one-dimensional subspace? Well, you just take, say, a vector. Think of that as a vector. And you look at its span. Okay. The line through it, in other words, all multiples of it. So let's say I call this the vector V, to use vector space language, then this line will be, we can represent it by that bracket V. So we can think of that as being the same as bracket of lambda V. What we want to do is we want to understand what are all the one-dimensional subspaces, or how do we visualize all the one-dimensional subspaces. Well, it's not too hard if you do sort of the same trick that we did over there. When we're looking at this, one way of thinking about it is in terms of a second line that lies above. Say, in this case, y equals 1. So over here, we could think about, say, the line where w equals 1. Okay. If w does not equal 0, then the line through ZW equals the line through, well, maybe I should write it this way. The line, okay, I'm using brackets in different ways. Maybe I'll use pointed vectors to make round brackets for vectors. So, all right, that'll be the vector, and that will be the line of that vector. Yeah, that'll be the line of the vector. So then this is the same as z over w, comma 1, because we can multiply by 1 over w. So all those subspaces are indexed simply by a single complex number. And most subspaces are of that form. But there's one extra subspace that is not included, and the extra subspace is the line through the point 1, 0. And you can multiply that by any complex number. All right, so that's our point at infinity. And when you put C together with infinity, we're getting again, topologically, the sphere. So over here we got a line with one point made a circle, but now we're getting a plane with one point. That makes a sphere. So P1 of C is a sphere. Next time we'll talk about other two-dimensional surfaces. The story will get richer. See you then.